Yeah, we can see it. Yeah.
Yeah. Thanks, Miguel, for the introduction and the invitation. Really happy to be here. So self-distillations as instance-specific label smoothing. So I choose this, I mean, one of the motivations to present this paper, it was because long time ago when I was using knowledge distillation, it was really interesting to see how it can help to get improvement performance. But the only drawback is that it's too hard to explain why your method is working. So it's nice to see these kind of words that are trying to explain and try to dive some insights of why this kind of methods works. So yeah, in this presentation, first I want to give an introduction of what knowledge distillation is, a very brief overview of some methods based on knowledge distillation. Then I will continue with self-distillation, that is the specific topic of this paper, and then I will continue with the contribution of this paper, which basically aims to, as I said before, to explain why the increase in performance when using knowledge distillation. So yeah, a little bit about knowledge distillation. So it started with a paper of Hinton at 2015, and the idea at the beginning, it was model compression. So if you have a model what you know is performing well, but this massive model which is too huge to, for example, storage in a mobile device, or you are having problems with the storage or computational resources. So it would be nice to have a small model. So yeah, the whole idea was to transfer the knowledge from the big model to the small one. This is usually known as a teacher-student training scheme. So yeah, in the original paper, I mean, what they try to, the way they try to transfer this knowledge is through the outputs or the logics of the teacher model. So once we have teacher model trained, we can use the outputs given some input data, and we can use that outputs to train our small model. So this is basically the general idea of knowledge distillation at the beginning. So, but then knowledge distillation evolved, and some variations appear, and yeah, many methods trying to use this this idea to apply it to different not only applications, but also to try to get some improve the performance of models. So when doing some brief overview of the methods in literature, basically there are, I mean, we can cluster those in two groups, which basically divide in two aspects. The first one is which knowledge is being transferred when using knowledge distillation, and the second is which strategy you will use to do this. So yeah, let's start with the kind of knowledge that is being transferred. So there are basically, again, three subgroups. The first one is called response-based knowledge. I took this actually from, there is like a review of knowledge distillation that it was, is this paper. It's really nice if you want to have a better understanding of all of these methods. But I pick up what I consider the most relevant. Yeah, as I say, in this group, I mean, we're trying to see what is being transferred, right? So this is the first one. The response base is basically the original idea of Hinton, which is, as explained before, if we have a pre-training model, we can use the outputs. In some way, we can soft these outputs, make it smoother. And we can use here these outputs to train a student model to try to guide the learning. So yeah, this was the very initial idea. So as you can see here, one of the problems that it has is that your student model performance will depend on the teacher model performance. So yeah, so then appear another kind of methods, which basically are instead of try to match the outputs or the logics of the teacher model, they try to match the in between, I mean, the intermediate layers. The idea is the same. I mean, we use some kind of metric or measure that try to match both these future representations. But if we go back to the original idea, which is go from a bigger model to a small model, so then you have to take into account some considerations like the number of, I mean, the size of the layers will be different, so you have to do some transformations. So it's the only drawback. I'm not very familiar with this, but apparently the papers that apply this kind of approaches show some kind of improvement by distilling the intermediate representation. So yeah. Finally, there is a theory group which basically try to match the instant relationships or some, yeah, it can be even of the relation between the samples that appear in the teacher, or it can be the relation between the layers that appear in the teacher. So you try to get some function between those, and your student will try to replicate these instance relationships. Yeah, that's all regarding to what kind of knowledge you want to transfer or to match or replicate. But there is another division which is quite important, and is the strategy used for knowledge distillation. So as Hinton proposed, I mean, the original idea is offline. So once you train your teacher, you can just use it to get the outputs in your data. I mean, your outputs will be like your new target, your new data. You even can save this outputs and storage in some place and don't use your teacher again. And your student will be trained based on this target. And then appear some methods that try to do something more. I mean, the problem they're trying to overcome is basically that when you use an offline method, your transfer will be depend in the original, as I said before, in the original teacher performance. So if your teacher doesn't perform well in your data, for example, you cannot get more than that, right? So then appear these kind of methods, which are called online distillation, and they just try in the training process to try to go back and forward. I mean, train the student, and with the response of the students, try to improve the performance of the teacher. Finally, I wanted to point this one because this apparently doesn't need a teacher. So your teacher is your student and your student is your teacher. So you try here to how to learn, basically. So based on some kind of rules from your previous training, you try to update your uh, your uh, your parameters in the current iteration. This can be tricky, actually. I also not familiar with these ones, but in this group also appear the kind of method that the paper I will talk about is about. So basically, in the previous methods, we see that the whole idea was basically trying to get a smaller model, right? Try to do model compression. But in self-distillation also, you can put there the methods that even they use a teacher and a student, the student is the same size and the same architecture as the teacher. Why that becomes relevant? Because when people start to do that, they realize that the student overcome outperform the teacher. And that's quite interesting because even if they are the same architecture, why using this self-distillation or this uh, strategy of training will improve your teacher, will improve the generalization of your models. And that's why, yeah, basically the paper tried to solve. Yeah. Yeah, so in self-distillation, there is a very famous method that is called born again neural networks. As I said before, now the idea is that teacher and student have the same architecture, the same number of parameters, everything is the same. And the idea is just to get an increase in performance. So the born again neural networks, basically what they want is do an iterative process. So you start with your teacher in step 0. And once you train your teacher, you train a student, right? And then your student becomes the teacher for a second iteration of the model. And you can continue in this way as many steps up to one. Okay, in the paper, they also suggest that if you want even a bigger or more consistent results, try an ensemble of methods. But the whole idea is until here. I mean, by using your new student and give it a role now from the teacher for the next iteration, you can start to increase the performance because you already know that you're under the knowledge distillation scheme, you can increase the performance of your initial teacher, right? So yeah, so now I will show a little bit now because this will be needed for the next part of the paper. So this is basically the maths behind knowledge distillation. So if we want to use a traditional knowledge distillation scheme, was basically you first of all you need a supervised training loss. This is basically cross entropy. You have your run through labels, and you can see this is basically the form. This is basically the equation of cross entropy. So when it becomes to distillation loss, the process is quite simple. So basically, as is replace the ground truth labels by the outputs of the teacher model. So you have now a teacher model which have same architecture as your network you want to train. Yeah, and you use these outputs as your new targets. There is a concept of temperature here, which basically smooth the relation or the yeah, the relation between the outputs of the logics. And yeah, so this is basically the distillation loss. So to train your model, you use both. You weight by some parameter here. But actually, I have seen a lot of papers that give a very high weight to the distillation, loss. So what I'm trying to say is basically that the full supervised loss is diminished. So it's trying to reduce the influence on the learning process. Okay. So the question, I mean, because yeah, it's kind of interesting, right? I mean, they are the same architecture, and your student is outperforming your teacher. So even in the original paper, I mean, the Hinton paper, they try to explain why this could work, right? And the intuition was that when you're training the outputs in the logics, the amount of information is higher, right? Basically, is what we can see in the figure here is what basically is happening. You train your model with hard labels, with a very sharp distribution in your labels. So your zero is, I mean, if these bars represent the logics of the output of your network, your zero is a very true zero, and your one is very true one, right? Once you use the output of your network, you know those are probabilities, right? So your network will say, okay, now your zero is zero, but also have something from one, and the opposite for the one, right? So when you introduce the temperature parameter, what you can do is smooth these differences. So if your temperature is higher, the relation between both probabilities will be lower. So what is this doing basically is increasing the amount of information, right? And this is what Hinton calls the dark knowledge, which is basically what is being transferred. It's these co-label similarities that doesn't exist when you train a model with hard labels, right? And if you think about a little bit, when you start to train a model, for example, every model starts to give these soft labels at the beginning. And when the model starts to overfit, basically is because is becoming overconfident. So the difference between both, between the distribution of the labels will be sharper, right? So in some way, this is improving generalization. It's making a little bit the model more robust to overfitting. But these guys made some. Oh, sorry. Okay. These guys are also based on this, I think, in this idea, so that your teacher, what is really transferring is more information, more uncertainty, basically, and that the hypothesis these guys have at the beginning is that this increase in performance is directly correlated with the uncertainty in the predictions. But not only that, but also in the diversity of your predictions. And they do some empirical experiments that demonstrate in some way that this is happening. But not only that, they present a really nice approach, which try to formulate basically the teacher-student training scheme like a maximum appreciable formulation of the logics of your teacher. So basically try to using maximum appreciable estimation, try to get the logics of your teacher, and they realized that this at the end ended up in some kind of instant specific regularization. So a regularization in the outputs that basically is based on the input samples. So this is basically what it will give to the model some kind of diversity. And based on this formulation, they also, is interesting that they try to, I mean, as I said before, if you say that this instance specific regularization, you basically are giving some emphasis on the diversity of the outputs. So the maximum procedure formulation relates directly with another approach, well known that for label smoothing, which main objective is also try to increase the uncertainty of the predictions. And yeah, once you have this this kind of similarity between this formulation and label smoothing, they realize that the only thing missing in label smoothing is the increase the diversity of the outputs of the model, and they impose on rule to implicitly apply this. And basically, they conclude with that, and yeah, as we can see later. So yeah, I will talk about now about the empirical findings. Yeah, so first, as I said before, they try to, I mean, the first hypothesis is the increase is related with the amount of information of uncertainty in the outputs of prediction, right? So this is actually straightforward to compute if you want. I mean, if you have a teacher and you have your data, you can basically use some information measure, like they use Shannon cross entropy to measure the amount of information that your teacher provides over a set of samples. So they call this the average predictive uncertainty of your model. So this is the first metric they will use to quantify the uncertainty of your model. But as the second hypothesis is that there is something else, because, for example, label smoothing can do this predictive uncertainty, can improve the amount of information of your outputs. Knowledge distillation is better. So the reason because it's better is because they hypothesize that is because of the amount of diversity that your teacher will produce in your data. So they, for measure that, they use confidence diversity, which if you think, I plot here as probability simplex space, but this is a very simple one. This is, I think this is two-dimensional. But anyways, so the idea is your logics in your teacher belongs to this space, so this kind of a space. So to be diverse, what you want is that your output spreads along this function here, right? So as to put in simple words, you want for a set of samples, if we are classifying zeros and ones, or you want that your ones be as diverse as possible. That means, for example, a one can be 0.7, 0.5, 0.4, and numbers in between, but as more diverse as possible. And the same for the zeros. I mean, will be below 0.5. So this is what they call diverse, because an overconfident overfitting, a network that is overfitting will produce similar values, right? A 1 will be always close to some value, close to 1, and a 0 will be always very close to 0, right? So yeah, so basically, theoretically, the way to compute this diversity is compute the area under this curve. This is this is 2D, so it's manageable, but imagine you are segmented 10 classes, will be a 10-dimensional. So it's kind of hard to handle. So they, in the paper, if you look at that, I didn't see in detail that part, but they use some strategy based on KN, I think nearest neighborhoods that they use to compute. But what I want you to take home is that is basically you want to try to increase the amount of spreads around this area, right? Okay. So based on these two metrics, so they do some experiments. So first, let's start with the method, the model I was talking before, the born again neural networks. So basically, they train a teacher. I mean, under this scheme, they train a teacher and a student for 10 generations. And they observe, I mean, 10 generations means that your teacher train your student train your another teacher, your student becomes your teacher, and your teacher train a new student, and that 10 steps, right? For that experiment, they compute the metrics, the predictive uncertainty, and the confidence diversity. Yeah, basically they realized kind of correlate, right? As the number of generations increase, the amount of information in your logics, in your teacher logics, increase, right? So yeah, so in some way, the distributions between the labels start to be more similar. That's basically what this uncertainty is trying to say. But not only that, also the confidence diversity. So your end teacher or your end student will provide more diverse set of outputs. Yeah, it's not, I mean, for me, it's, I mean, they say that it's directly correlated, but you can see in the test accuracy, you can see that there is a trend to increase the performance, but it's still there is some highs and lows. So yeah, but the point here is that, yeah, as more generations you train, your model became more uncertain, and the diversity in the logics it's higher. Yeah. Then they try another experiment that is just basically instead of trying different these born again neural networks, they just use one teacher and one student, and they try to modify the temperature. So as I mentioned before, the temperature as higher as, I mean, this is the amount of information here will be a bit obvious, right? Because as higher the amount of information, as higher the temperature, as higher the amount of information. Yeah, as higher the amount of information, basically. No, sorry. It's the opposite. As lower your temperature, more similar the similarities between the logics is, and then your uncertainty increase. So yeah, that's the correct way. But look what happened with the diversity. So as they increase the temperature, the performance of the model increase, but then it starts to plateau at 2 basically. But they realized something similar happened with the confidence diversity. So and also with the calibration over here. By the way, you can see my mouse now, right?
Yes, yeah.
Okay. Yeah, you can see the calibration error also have direct correlation with this point here and this point here. I mean, kind of, but that's the point. Yeah, if you think a little bit about it, it's also a bit expected, because at some point, if your temperature is too high, what will happen is that all the classes will be almost the similar, right? So it will not be such a diversity in the outputs, right? So that's why it happens. So the diversity in the logics plateau, and then here the accuracy of the model is also stable at that point. So basically, yeah, they are proving that what knowledge distillation is doing is basically increasing the uncertainty of the predictions, and it's also because of the diversity of the diversity of the logics. So this is all the empirical demonstration, I would say. But then they came with the maximum a posteriori perspective of self-distillation. So yeah, so the whole idea is try to predict or try to get the logics of the teacher based in a maximum posteriori estimation strategy. Yeah. So yeah, for I mean, the whole idea is that they want to demonstrate that the logics of the network can be regularized by the they can be regularized by a function of something that depends on the input, on the instance, basically. So yeah, I will not look into. I mean, I will not go too much into all the maths, because I started to do it by hand, but at some point I feel like I needed more time to go through it. But I mean, I think the whole point, it makes sense, and yeah, let's see. So yeah, so the first assumption they want, I mean, they have, is that the probability of your targets you want, I mean, the hard labels you have, given an input instance is a categorical distribution of your logits. Those are the logits of the teacher. So this is as normal. I mean, we can do that assumption when we are training in a supervised fashion. But then they say that okay, and you can assume that your probability distribution of your logits given X can be modeled as a direct distribution, which depend on parameters based on the input instances. There is a closed form solution for this, assuming this direct distribution. But the problem here is this doesn't depend on the labels, right? So this is not trainable, basically. It's not obvious how this can help to get a sense of regularization based on the input instances. So, but then what they basically said is, what if we can model? We can see that the training, I mean, training the student as a maximum posteriori estimation. So this is basically bias. The first line is basically bias. If you want to estimate the probability this C given X and Y, given X and Y, and of course the parameters dependent on the instance. So you can get by bias, which is basically the multiplication of these two probabilities, but by properties of logarithms, so you can divide it. So this gives more the sense of a regularization formula, right? Equation. So yeah, so this first term here is basically train a student network. So the direct, I mean, if you are using maximum likelihood estimation, the direct translation is basically, yeah, go through cross entropy here. Remember, it's instance based, right? So it only depends on the label of the instance at the moment. And then for the probability distribution of C, given X and the parameters of the direct distribution, it's a bit trickier. So they just give it expressed in terms of direct parameters, right? So, but then they can divide and they can say that this is just train a student, and this is some kind of regularization that depends on the instance here, of the instance, or of the input instance. So this is basically what they want and what they try to elaborate in detail in the next step. So we have now, yeah, a classic form of regularization here, where this depends on the input instances. Yeah, so I think here they did a reversal approach. So first they try to get rid of the instance information here. I mean, assuming that the probability of the C given X is just a uniform distribution. If you do that, basically you are saying it's not depending on the instance. All the labels will have an uniform distribution, which is basically a scalar number. But if you translate this to the, I put here this formula to not get lost. And yeah, you basically translate this, yeah, the direct parameter distribution, you translate and you put in this formula here, you can get this form here. And if you see here, you have again a cross entropy here and your regularization term that is here, but you can see your regularization term now is a scalar of the logits. So this is basically label smoothing. That is, in label smoothing, basically what you have is you have your hard labels and you divide or you multiply your labels for some scalar to make it smaller, right? The original idea was that if they are smaller, they are easy to learn. So basically by assuming that the relay, yeah, by assuming this distribution is uniform here, they basically get label smoothing. But that's not what they want, right? Because as I said before, label smoothing is good because it provides some uncertainty in the predictions, but it doesn't provide diversity in the outputs, right? So now what they want to do is to include that. I mean, to try to include this information of the input instance. Yeah, please ask if you feel, because I thought when I read this, it was quite heavy. So, okay, I will continue. Yeah, so now, yeah, I said before, they want to include in the regularization term this instance-based or instant-dependent term. So assuming you have the probability of, I mean, again, this is the probability of basically what you get from your network when you train it. And you assuming it's a categorical distribution, you can just model as a, yeah, as a normal you do as a softmax of the output of your network. Yeah, this is notation here to basically, yeah, the conversion from softmax to the exponential form. The brackets, what highlight is that you pick the label of the sample I mean, the label you are saying here. I mean, because it's a vector of the logics, you focus just on the one you want. Is what the brackets mean. Yeah, but then for some properties of the direct multimodal distribution, they also can say something like that the marginal distribution based on the X on your input, but conditional on the parameters of the direct distribution, can also be modeled as a categorical distribution of your parameters here, or the parameters of your direct function. So, and here is the trick that I use. So, because when you normalize these parameters here, they resemble to this function here. So then, yeah, they assume that these parameters, dependent on the instance, basically are the excitation, not excitation, are the outputs of the teacher model. Your logics, and because of you want, I mean, because if you later here, they will need some kind of variance here. That's why they need the B and the gamma here. Yeah. So, but the important point here is that they have here they have a representation of the parameters of the lake distribution based on your student, based on your teacher logics. And this is basically something similar at what they want. So another trick here, I mean, I consider it's a trick. So they give to this value here 1 just to eliminate the previous one here. And yeah, and if you replace again in the function before, what you get is basically this form basically here, that you have again cross entropy here, but you have here the priors of your, I mean, the distribution of your logics based on this instance dependent term, which is basically a weighting scheme. They do some trick here because you basically put this function here, and you can do it that by hand. So if you put that function here, you will get this here, right? But how, because this is not dependent of this C here, you can just take it out. And then it resembles to a weighting. So basically what this form tried to say is, okay, you have your outputs, your logics, which are weighted by a term that is based on the instance, the input instance. So yeah, that is basically what they want at the beginning, to try to prove that the priors of your logic, of your teacher logic distributions depend in a term based on your input images. So yeah, you have a regularization term here then, which basically mathematically proof, but apparently I don't know why they didn't try this way for training. They still for the next experiments they try the traditional knowledge distillation strategy. So, but yeah, wait a second. Yeah, you got then this nice equation that represents a regularization based on the instance, right, in the input instances. But before you have, as we saw before, this regularization term, if the distribution or your logics, it's modeled as a uniform distribution, is label smoothing, right? So, I mean, the idea they have is the only thing you need for label smoothing to improve the performance is to try to increase this diversity by this term dependent of the parameter of your input instance, right? So they try to do that. Basically, they include a term for your label smoothing equation. They include a term that depends on the input instance. So the solution they have is simple, or kind of simple, I will say. But yeah, so basically what they do is when they are trained, I mean, you already decide how you will smooth your logics. You can assign some scalar and just multiply it by your logics. But they want that to vary depending of the input image, right? So basically what they do is in a batch, they try to measure the uncertainty of the variation given for those samples in the previous epochs, and for for the samples where the uncertainty was higher or they were less confident, you just apply a higher smoothing, basically. For those which is very confident, the smoothing is lower. So it's basically a trick what they do to do a little bit more smarter label smoothing, or to try to include what they found, right? That is not only the uncertainty, what it gives some increase in performance, but it's also the diversity that your model is able to provide. So then, yeah, they tried all of these methods. Basically, they tried, I'm explaining here. Okay, each column is database, and the first row is and they have each column is a database, and they have different models here, right? Yeah, they have two different models here. That's what they have. Oh, they have more. Okay. But in all of the experiments, you can see, okay, they have the traditional cross-entropy training, which is basically based on hard labels, supervised, the traditional way. The label is muting. The label is muted plus this additional term that gives some diversity, and knowledge distillation based on temperature. I mean, it's not the bond again, it's based on temperature. And you can see in most of the cases that the accuracy given by knowledge distillation was really superior in most of the cases. I will talk later about the calibration of it, but yeah, the accuracy was superior in most of the cases. What is interesting is to try to see to compare both the label is muting and the label is muting plus this term, or the beta smoothing, what they call. Again, there is some gain in some cases for the label is muting plus diversity. So proving again that is an important term to try to teacher to be diverse, or what they try to prove actually, that your diversity in your teacher is directly correlated with the performance of your model. Yeah, label smoothing even is better than in some cases than or most of the cases than cross-entropy. It's still no, it's still no as good as both of the other approaches. When we look at the calibration errors, it becomes a bit interesting, right? Because in some cases we can see that even self-distillation and knowledge distillation achieve higher calibrate, or lower performance in that case, and it's a bit not obvious, but you can expect that, because basically when you are increasing the uncertainty and you are giving more diversity, basically what you are doing is becoming your model less confident. Even the accuracy is high, your model is still it can be still less confident compared with the others. So it's a trade-off that you have to take into account. Yeah. So they conclude basically with those experiments here, which basically prove empirically that the increase in performance, it depends on, again, in the diversity of your predictions, and also in the amount of uncertainty of information they provide. which was also proved mathematically when they do the demonstration with the maximum a posteriori estimation. So yeah, that's all.